Welcome to the ninth lecture of module 4. In this module, we are discussing reactor design. Before going to this lecture, let us have brief recap on our previous lecture. In the last lecture, we have covered mainly irreversible first order reaction in series, and under which we have quantitatively discussed the product distribution, and then we have quantitatively obtained the product distribution from the red equations. We have considered two different cases. One is plug flow reactor or batch reactor, and other one is the mixed flow reactor MFR. Then we have considered different order of the series reactions, like first reaction is first order and the second reaction is 0 order, and then we have considered first reaction is 0 order and then followed by first order reactions. In these combinations of reactions, we have seen how the product distribution changes. In this lecture, we will consider design for reversible and series parallel reactions. So, the brief outline of this lecture is reversible reactions, two step irreversible series parallel reactions, under which we will discuss the product distribution, qualitative discussion on it, and then we will consider quantitative discussion or quantitative treatment of product distribution for two different cases. One is batch reactor or PFR, and the second case is mixed flow reactor. And then we will see the graphical representation of this quantitative treatment. Let us consider reversible reaction. The reversible reactions are quite cumbersome to treat them analytically or treat them quantitatively. So, we will briefly discuss about the product distribution qualitatively. Let us consider first order reversible reactions. Of two types, one is A to R to S, and in other case say B to T to U. So, the concentration profile in a batch or plug flow reactor, we can write for this series reversible reaction, like we have seen. If we consider typical case of A to R to S, and both K1 and K2 are of unity say 1 1, we can write the product distribution concentration versus time. If we do, we have seen that the concentration of A decreases gradually and concentration of R increases and then decreases, and concentration of S initially formation is low and then it is increases. This is the concentration. So, this is concentration of A, this is concentration of R, this is concentration of S. Now, if we consider this reaction, reversible reaction, the concentration profile would be so A to R to S, these are of equal rate constants. So, concentration of A will decrease, concentration of R will increase, and concentration of S initially very low and then it will increase and will reach like this. So, the concentration profile, this is for A, this is for R, this is for S. So, we can see that in this reversible reaction, when the rate constants are of equal, in that case the intermediate R, it does not reach to the maxima. So, it gradually increased and remains constant after a certain time. So, it very slowly increases, but it does not come down. So, it does not reaches the maxima. Now, if we consider this reaction, we know the for the parallel reaction how the concentration profile look like. For A to R to for B to T and U. So, this is 1 and this is 1. So, the concentration profile would be B will decrease and R and S will be almost similar, reaching like this. So, this is for B and this is for T and U. Now, if we consider the case which is given, so the concentration of B would decrease and concentration of R and S would increase and it will not cross. So, this is the concentration profile for B and this is for T and U, and in both cases we have seen the intermediate does not reach to the maxima. Now, let us consider two step irreversible series parallel reactions. So, in this case, if we consider the general case, say A plus B forming R with a rate constant K1, then R is again reacting with B forming S with a rate constant K2. So, this is a set of reaction, and we assume that the reaction, these two reactions are irreversible in nature, and this is of bimolecular type and at constant density system. So, our assumption irreversible reaction. Second thing is bimolecular, and third thing is constant density system. Now, if we based on this, if we write the rate equation, based on this, if we write the rate equation, we can write the expression as R A is equal to d C A dt, which is equal to minus K 1 into concentration of A into concentration of B. So, C A C B. For rate of reactions of B, we can write R B is equal to d C B dt, which is equal to minus K 1 C A C B. Again B is reacting with R forming S. So, here it would be minus K 2 C R C B. For the rate of reactions of R, we can write R R is equal to d C R dt, which is equal to K 1 C A C B, because R is forming in the first reaction. So, K 1 C A C B, and then R is reacting with B in the second reaction. So, which is minus K 2 into C B C R C B. Now, for S, which is forming from the second reaction, we can write R S is equal to d C S dt, which is equal to K 2 into C R and C B. K 2 into concentration of C R and concentration of B is C B. So, these are the four rate equations. We can see from this, or we can write from this two step irreversible series parallel reaction for constant density system. Now, if we qualitatively see how the product distribution changes, we could see three different cases. In the product distribution, whether should it make any difference in the product distribution how we mix A and B. So, we would see whether addition in different way between A and B changes the product distribution. Let us consider addition of A slowly to B and see qualitatively how it happens. Now, let us take a beaker where we have B initially in the beaker, so component B is taken in a beaker. Now, take another beaker filled with A. So, this contains component A. Now, it is added slowly to this beaker. So, consider the reaction or addition of A into the beaker B in such a way that a small bit of addition of A into the beaker and with continuous stirring, we should make sure that all the A is used up. So, as soon as all the A is used up in this beaker, so product R will form. So, as per the reaction, A plus B forming R with a rate constant K1. So, as long as small bit of A is added to this beaker, this B reacts with A, forms R and the reactions become complete. But as long as R is formed, this small bit of R find excess B in the beaker. So, that R immediately reacts with B and forming S with a second reaction. So, finally, the product which will obtain by the addition of A, small bit of A is product S with no R present in the mixture. So, the concentration profile in this case would be like this. So, concentration of B moles of A added. So, initially as small bit of A is added, B will be used up and finally, all the B will be used up. As soon as B will be used up, further addition of A would produce would remain only A. So, this is the concentration changes of component B, this is the concentration changes of component A which will again increase, and the product which will form is S, and then since there is no all the B used up, so it will remain constant. So, this is the profile of S. Now, let us look into the another way of adding A and B or mixing A and B. If we add B slowly to A. So, in a beaker, if we take so, this is containing B, this is containing contains A initially and addition of B is slowly done in a beaker contains A with continuous stirring. Now, let us see how the product distribution changes in this case. Now, as we know the reaction A plus B produce R with a rate of reaction K1. So, as we add small bit of A of B into A, then A will react with B to go for completion of reaction forming R. So, we will have R in the reaction and this R will not find any B initially and hence it will not produce S. So, as we add on slowly the B, more R will form and then A and R both will compete to react with B by slowly addition of B into A. So, R will find excess of B and then it will produce the second reaction to produce S. So, the product distribution in this case would be A will be U stop and R will form and S initially very low and then S will increase. So, this is as we can see the delta B, this is delta B which is B naught minus B. So, moles of B consumed during the reaction is this side and this is concentration of the material in the mixture. So, this is the concentration of the material in the mixing tank. So, this is say 0 and this is say 1 and this would be 2.0. So, at 2 delta B is 2, all the A will be used up and this is the concentration profile for R. R will reach maxima and then it decrease to 0. This is concentration of A and this is concentration profile for S. So, that is how addition of B slowly to A will change the product distribution between no addition of B into A or A into B. So, if we add them differently, the product distribution changes. Now, let us consider another case where we can add both A and B simultaneously. If we add both A and B simultaneously and mix them together, we obtain, say, this is our mixing tank, and we have so we can add both A and B component into the beaker. So, contents mix uniformly before they reacts. So, the reaction is A plus B2 R with a rate constant K1, R plus B to S with a rate constant K2. Now, if we add A and B together, what will happen? Initially A will react with B and produce R. So, this R will initially will find very less, this R will find B is present. So, A and B both will compete to react with R. So, both production of R will happen and at the same time S will produce. So, it will give the similar concentration profile as we often for the second case, the addition of B into A. So, if we add an A and B simultaneously, the product distribution would be same as that of addition of B slowly into a container containing A. So, the product distribution for this case would be like this. So, this is for A, this is for R and this is for S. So, the product distribution is similar to the earlier case. Now, from this qualitative discussion, we have two major observation. Observation 1, when A is kept uniform in composition as it reacts, then R is formed. So, we can see R intermediate is formed and fresh A is mixed with partly reacted mixture, then no intermediate R is formed, which is the first case which we have discussed. We have taken fresh A is mixed partly reacted mixture, then intermediate R is not formed. So, this is the typical trend of reaction in series. So, this is the A to R to S with addition of B in each of the reactions. So, that is called behavior, typical behavior of the series reaction. In the second observation, we can see if we keep the concentration level of B, whether it is high or low, whatever concentration we can keep, there is no effect on the path of the reactions and on the product distribution. As we have seen, if we add A B slowly with A and both A and B together, then the product distribution does not change. So, this indicates the behavior of reaction in parallel. So, it indicates B to R to B to S with addition of plus A and R, with addition of A and R to different reactions path it follows, and so it considered as parallel reaction. So, the general rule we can write: irreversible series parallel reactions can be analyzed in terms of their constituent series parallel reaction, and the optimum contacting for favorable product distribution is the same for the constituent reactions. So, we can treat the series parallel reactions which can be analyzed in terms of their series reactions as well as parallel reactions, and the optimum contacting pattern would be similar to their individual constituent reactions. Now, let us quantitatively discuss the product distribution for two different cases. One is batch reactor and PFR, and second case is the mixed flow reactor. Now, let us consider the earlier reactions, that is A plus B forming R with rate of reactions K1 with rate constant K1, R plus B forming S with K2. So, here we consider R is the desired product, and assumption is that reaction is slow enough so no reaction takes place during mixing. Now, for this case, let us write R A is equal to d C A by d T, which is equal to minus K 1 C A C B, and R R is equal to d C R dt, which is equal to K 1 C A C B minus K 2 C R C B. Now, if we divide these two rate expression, we obtain R R by R A would be equal to d C R by d C A. So, this would be equal to K 1 C A C B minus K 2 C R C B divided by minus K1 Ca Cb. So, this we can simplify would be equal to 1 minus 1 plus K2 by K1 Cr by Ca. So, the solution method of this is already discussed earlier. Now, if we assume no R present in the feed, that means Cr naught is equal to 0 initially and Ca initially present is Ca naught. So, we can integrate and get the solution of the differential equation, which is Cr by Ca naught is equal to 1 by 1 minus K2 by K1 Ca by Ca naught to the power K2 by K1 minus Ca by Ca naught. This is valid for K2 by K1 not equal to 1. So, for K2 by K1 equal to 1, we can write Cr by Ca naught is equal to Ca by Ca naught ln Ca naught by Ca, and this is for K2 by K1 equal to 1. So, these are the concentration profile of R or relations between Cr and Ca. Now, the maximum concentration we know how to obtain, which we have discussed earlier, just differentiate it and set it to 0. So, you will obtain Cr max by Ca naught would be equal to K1 by K2 to the power K2 by K2 minus K1. This is for K2 by K1 not equal to 1, and Cr max by Ca naught would be equal to 1 by E, which is equal to 0.368, that is for K2 by K1 is equal to 1. So, this is how we can obtain the relation between Cr and Ca. At the same time, we can calculate the maximum concentration of intermediate which is obtained. So, from this we can calculate the optimum concentration or maximum concentration of Cr can be obtained at different ratio of K2 by K1. The concentration for other species for a plaque or batch reactor we can obtain from the component balance. So, if we do the component balance over A, we can get Ca naught plus Cr naught plus Cs naught is equal to Ca plus Cr plus Cs. From here we can write delta Ca plus delta Cr plus delta Cs is equal to 0. So, from here we can put the relations between R and A, Ca, Cr and Ca, and we can obtain the Cs as function of Ca, Cr. Now, if we do the balance, over B, we can obtain concentration profile for Cb. Now, let us see the Levenspiel plot for different K2 by K1 values and different Cb by Ca ratio, how the product distribution changes or how the product distribution can be calculated from the Levenspiel plot for series parallel reaction in a batch or plug flow reactor. So, in this case you can see this plot shows the at different K2 by K1 values how the changing with the mole fraction or conversion of A changes the product distribution. So, the y axis is Cr by Ca naught, which is shown over here, and this lines this at shows the delta Cb by Ca naught. So, at delta Cb and Ca naught values, these are plotted. So, to obtain this plot, this is plotted based on the equations we have derived. So, kinetically we can calculate for a particular reaction K2 by K1 values we can calculate. So, this is can be done from the experiments. So, if we take different ratio of B by A in a batch reactor. And allow the reaction to complete. So, then we can obtain for each run we can obtain K2 by K1 values. The best ratio delta Cb by Ca naught would be when it is 1. So, you can see that means delta Cb minus delta Cb by Ca naught is approximately equal to 1. If we look into this curve over here, you can see the K2 by K1 values, they are far apart from each other. So, this would be the best ratio to be considered for the reaction. So, with a known K2 by K1 values, what we need to calculate K1 from kinetic experiments. How we can do from the kinetic experiments K1, how we can obtain? If we take large excess of B and then follow the disappearance of A, take large excess of B and find the disappearance of A. So, this will behave like a first order reaction. So, we can obtain K1 values. So, that means it is pseudo first order reaction. So, we can calculate K1 and with that we can calculate K2 as well. Let us take an example. Consider the following elementary reactions, that is A plus B to R and R plus B to S, with the example which we have considered. 1 mole of A and 3 moles of B are rapidly mixed together. The reaction is very slow, allowing analysis of the composition at various times. When 2.2 moles of B remain unreacted, 0.2 moles of S is present in the mixture. What should be the composition of the mixture A, B, R and S when the amount of S present is 0.6 mole? The second problem is that 1 mole of A is added bit by bit with constant stirring to 1 mole of B, left overnight and then analyzed. 0.5 moles of S is found. What can we say about the K2 by K1 values? And the third problem is that 1 mole of A and 1 mole of B are thrown together and mixed in a flask. The reaction is very rapid and goes to completion before any rate measurements can be made. On analysis of the products of reaction, 0.25 mole of S is found to be present. What can we say about K2 by K1? So, in this case, at the start of the reaction for the first case, so at start A naught is equal to 1, B naught is equal to 3 and B we can write Ca naught, Cb naught and Cb is 2.2 and Cs is 0.2. Now, we can do from the material balance, we can calculate delta Cb minus delta Cb would be equal to 3 minus 2.2, which is 0.8. Now, if we consider this figure, we have to find out this point. So, this is the line for 0.8 delta Cb by, so here we can write minus delta Cb by Ca naught is equal to 0.8. So, we can locate this is the curve. So, this is for delta Cb by Ca naught is equal to 0.8. Now, we have to Cs is given 0.2. So, following this line we can locate 0.2, which is this one, this is the distance of delta S, this is C s, which is equal to 0.2. So, with this we can obtain this point, which is K 2 by K 1, which is equal to 0.85. So, once we obtain K 2 by K 1 0.85 over here, now we can follow this curve. This will be over here. So, then we can take this is 0.6, S is 0.6 at this value. So, since finally CS is equal to 0.6 finally. So, with this 0.6 we can locate at this point, we can calculate A, CA would be 0.1, CR would be 0.3 and CS is given 0.6, and B, CB would be equal to 3 minus 2 into 0.6 minus 0.3, which is equal to 1.5. So, we can obtain the composition of the mixture, that is A, B, R and S. Now, for the second case, 1 mole of A is added bit by bit with constant stirring to 1 mole of B left overnight and then analyzed, and often 0.5 mole of S is found. And what can we say about K 2 by K 1? From this we cannot say. So, solution of B, we cannot obtain any values of, or we cannot say anything, nothing can be said for K 2 by K 1. Now, if you consider C, which is 1 mole of A and 1 mole of B are thrown together and mixed in a flux, the reaction is very rapid and goes to completion before any rate measurement is made. So, we have it is given, so 0.25 of S. So, this is 0.25, which is over here, we can calculate. So, this is S is equal to 0.25 and with delta Cb by Ca naught is equal to 1, because 1 mole is added to 1 mole of B. So, since this is 1, we will follow this line. This is the value of Cs is equal to 0.25 and we can obtain K 2 by K 1 is about 0.4. Since the reaction is very rapid and are actually formed less, then what could be formed? So, this K 2 by K 1 is the upper bound. So, we can say therefore, K 2 by K 1 is less than equal to 0.4. Now, if we consider mixed flow reactor, we can write the design equation as we have done before. Tau m would be equal to C A naught minus C A divided by minus R A, which is equal to minus C R by minus R R. From here we can write tau m is equal to C A naught minus C A divided by K 1 C A C B for these reactions A plus B to R, R plus B to S, this is K 1, this is K 2. So, this we can write minus C R divided by K 2 C R C B minus K 1 C A C B. Now, if we rearrange, from here we can write, from this we can write minus C R by C A naught minus C A is equal to minus 1 plus K 2 C R divided by K 1 C A. So, minus C R by C A naught minus C A is equal to minus 1 plus K 2 C R by K 1 C A. So, this is nothing but the difference forms of the differential equations which we have obtained earlier, that is d C R by d C A is equal to minus 1 plus K 2 C R by K 1 C A. Now, if we write C R in terms of C A, we can write C R is equal to C A into C A naught minus C A divided by C A plus K 2 by K 1 into C A naught minus C A, and we can find out maximum by the earlier procedure. So, we can write C R max by C A naught is equal to 1 by 1 plus K 2 by K 1 to the power half whole square. So, graphically we can see the Levenspiel plot for the mixed flow reactor. So, it is similar to the earlier plot as we have done for the plug flow reactor. The Levenspiel plot for at various K 2 by K 1 values and delta C B by C A naught, we can see the Levenspiel plot for the distribution of the products. So, thank you very much for attending this lecture, and we will continue our discussion in the next lecture.